and clustering. And I'm going to make some distinctions between the work we did last week and what we are doing today. But part of the focus of week 5 will be classification foundations, to give us some kind of foundation on classifications, evaluation and decision consequences, how we evaluate those results and the consequences of the decisions that we make. And then we'll look at clustering, which is a distinct thing from classification. We'll look at clustering and unsupervised learning. And then we will go into 5, which will be practice, capstone, and mastery check. And then week 5, deep dive. But my focus here is to go through what we have in screen 2, 3, and 4. And then we will proceed to our Jupyter lab to go through a couple of, at least one lab that would help explain what's going on.
Okay.
So, classification and clustering, predicting categories and discovering structure. So, classification essentially focuses on predicting categories, and then clustering is about discovering structure. Now, the mission of week 5 will be to extend our supervised learning from just continuous outcomes to categorical outcomes. As you were aware, last week our focus was on supervised learning, and where we did regression, and we talked about regression as often resulting in continuous outcomes, right? It would be, you have numbers like numbers on the number line, from anything from one end of the of infinity to the other end of infinity. It could be any number within that number line that would be the typical outcome. So these are usually continuous values that we get when we are doing our supervised learning using regression. But today we want to go beyond outcomes that involve continuous outputs to categorical outcomes, actually, where what we are trying to do right now is to group things together. For example, I'm trying to make a decision whether maybe someone I see on a camera is male or female, or whether we would have 5 balls that are balls of different colors, and we're trying to decide which of them is red, for example, right? That's a categorical outcome because we are looking at different categories and we're trying to choose one of many. So the second focus of week 5 will be the interpret classification errors. Now, sometimes when you make those decisions, we end up with errors, right? And we want to see how those errors are classified using confusion matrices and decision, and then we'll look at some of the consequences of the decisions that are made. And depending on what kind of problem you're trying to solve, a certain amount of error will be tolerable. So if I am working on a mission critical project, error might be less tolerable than, say, I'm trying to make sure my email doesn't incoming email into my email box, which is often classified as spam or not spam. In that case, if we have some spam emails come through, that's not a problem. But then if someone has to get early treatment for a disease condition, for example, cancer, and I make a mistake, right, in my classification, and I'm able to say to a patient, oh, based on my machine learning model, for example, oh, and every other information I have, you're free to go home. You don't have cancer. And then the patient goes home, gets home, all of a sudden, that's a problem because they are going home with the false belief that they are okay, but the cancer is not going to stop growing. And then the cancer might begin to grow and even metastasize before it's detected. And now all of a sudden it's too late. And then that will cost a whole life. That's an entirely different proposition from, say, my spam detector in my email, right? Being unable to detect certain spams. So that's where we talk about decision consequences, because in some use cases, right, decisions can have crazy consequences, and in some others, not as much, not as crazy. Um, those consequences might not be as crazy. So that would lead us into different thresholds, right, for what we consider as good or bad, accurate or inaccurate. In other words, the issue about accuracy thresholds is uh, it's not absolute. It is relative to the severity of the problems. And a lot of times, domain expertise is required in making a decision, that consequences might be far-flung out there, or consequences might not be very serious. And then we can, tweak around how we classify those errors and how we place our thresholds, what confidence we accept. So the third mission of this class will be to introduce unsupervised learning through clustering. Most of what we will do in supervised learning is where we have these features and then our targets, right? We need to know. In other words, I think I did give an example in the previous video where I was talking about if you want to train a child, and you want them to understand shapes, for example, or you need them to understand colors, you would give them an object that has a red, and then the child will say, this is red. And as you keep giving them the answers, they begin to associate.
Jupyter Lab
Right.
portion
They
of
begin to understand what
week 4.
they begin to understand what each of those things mean. So, but you also now have unsupervised learning, which is a situation where those answers are not provided, right? You provide a whole bunch of features and the system doesn't have the answers, but somehow the system is supposed to learn those things, right? So what the system does in this particular case, yeah, the algorithms we have are algorithms that would cluster those things, right? Because in this case, it's unsupervised. So all it does is cluster. So I'll give you a simple example of clustering. You walk into a room, let's say a Montessori classroom, and then you have shapes, you have toys that have 5 distinct shapes. Some of the toys are triangular in shape, some are square in shape, some are circular in shape, some are polygonal in shape, right? And you ask a kid to go in there and begin to put all the shapes, right? All the objects with similar shapes in different clusters or in different buckets, right? That's clustering. So that's what happens with unsupervised learning, where you give a system a whole bunch of objects or features, and then it begins to look for those that have similarities in their shape, in their color, in certain parameters, and begins to put them, or features, and begins to put them in clusters, right? as humans, when we have tons and tons of data, we might not even see those distinctions. But when you feed that to an algorithm, the algorithm is able to look at those patterns and then to cluster all of those objects. For example, put together all of those objects in different clusters based on the specific features or shared features that they have. So that's how supervised learning that's a very simplistic way of explaining supervised learning. And then the fourth mission here will be to learn why metric choice must match the problem context. The matrices we choose would have to match the problem context. And in talking about decision consequences, I kind of alluded a little bit to that. So the learning outcomes for today would focus on distinguishing regression. I kind of talked a little bit about that, making a distinction between regression where we have continuous outputs. We're going to contrast that with classification, where usually you have different categories and then you're supposed to choose between one or more categories. And then you also have clustering. Clustering is now where you put things in different buckets based on their unique or shared characteristics. Number two will be the issue of training logistic regression, K-near neighbor, what we call KNN algorithms, or decision tree classifiers. So these are different kinds of classifiers that we can use, we would look at today. Then we also want to, number three, interpret accuracy, different ways of looking at how correct or not correct your choices are, or the outputs or the results of our regression, classification, and clustering, particularly our classification and clustering, different ways of being able to interpret it. In layman's term, right, different ways of figuring out how accurate the results are. But again, when we come into classification and clustering, we use certain precise terms, right? Like there's a difference between accuracy and recall, or precision, F1 score, ROC, AUC. Will kind of look at those a little bit. Number four, we would also want to explain false positives and false negatives in context. Now, that's kind of alludes to decision consequences that we've talked a little bit about. And then the fourth outcome will be to apply k-means clustering and profile clusters, to problems and then identify the risk of over-interpreting clusters. So I'm going to start with classification foundations. So where we'll be talking about labels, probabilities, thresholds, and different model families. So classification versus regression. Like I mentioned, our last video focused more on regression, where our outputs are generally continuous outcomes, right? And then we want to contrast that with classification, which is more of the subject of today's class. So as you can see, there are different tasks that you can have. You can have a regression task, classification, clustering, and forecasting, right? So in regression, like I did mention earlier, the target, which is your ultimate result, is going to be some continuous value, right? So that's what happens in regression. And an example of a regression problem is where you're trying to predict the revenue or the temperature, or for example, you've been given a couple of features, right, about a house, and then the goal of the algorithm or the model is to predict the price of the house as you would agree, we are going to end up with some kind of tangible value. It could be $200,000, it could be $1 million, and all of that. So it could be 1,235,043 cents, right? That's a continuous value. That's what the outcome will be. But that's kind of different than when we are looking at a classification problem, right? In a classification problem, I'm trying to find out, okay, of 5 cars that I'm selling, which is it that people like most? And I can look at how I would find out which of the cars people like most is over a 1 month period or over a 1 year period, which of the cars are people buying more, right? That's a classification problem, right? And to do that, I need to classify each of those categories, right? So for classification task, my target is to get some kind of classification, categorical label. And then an example of that will be predicting churn, right? And churn here would refer to like losing customers, you know, I'm trying to predict, okay, look at these certain customer behaviors. What is the probability that I'm going to lose or not lose a customer, right? And based on a couple of inputs, the system can predict, yes, you're going to lose that customer in the next 6 months, or you are not going to lose that customer, right? It's not an exact science. And that's why we're going to eventually go into probabilities and all the other things that are used to really characterize the outcome or the output of a classification problem. Excuse me. So then we have the issue of clustering. I've kind of alluded a little bit to the issue of clustering. In clustering, you really do not need to provide any labels. What happens is you throw in all of the data you have to the system, and the system would essentially go in there and look for features that are common. So begin to put things in different buckets based on their similarities, right? That's what clustering is. So for example, I'm trying to find different customer segments. Let's say I have 1 million lines of data and I throw it into, feed it to an algorithm, right? I don't know how many customer segments there are. I'm trying to do some kind of segmentation of my marketing, right? And I want for the system to come up with different segments or even micro segments that I can target. All I need to do is feed it all of the data that I have. Obviously, that data does not have the categories, because if they had the categories, then I wouldn't have this problem. And you feed it to the system, and you'll be surprised that the system would actually look at different things, their buying habits, their age, their demographics, and all of that. And then all of a sudden, it will throw up different categories of customers, right? And put all of them with distinct labeling, right? It would output all of them, right, in little clusters, which you can now use to do your marketing. And then the last but not the least will be the issue of forecasting. And this kind of looks a little bit like what happens when we do time series and all of that. But we have these time boxed outcomes, and our goal is to eventually predict what happens next month. What's the demand going to be? And how do we predict it? By looking at time boxed outcomes from the past, between uh, January to February in the past 10 years, right? This has been the behavior of customers, right? Therefore, in the next 5 years, we're going to be predict that so and so will happen to the behavior of customers in January, February of 2030, of 2035, bearing all other variables, right? That's kind of what the forecasting is about, a bit of time series. And then this is a classification of different models. So we have, as you can see, these are examples of some of those models. And we've what we did in a previous video was we were talking about logistic regression, linear regression, and logistic regression. If we were to categorize all of these models, the models that are referred to as parametric models are models that have a fixed form and limited parameters. In other words, we have a fixed number of parameters and we're working with those parameters. And you can see those kind of models are like linear and logistic regression. But then we have non-parametric models, and these models are models that are really very flexible. You don't need a fixed number of parameters. Your parameters can actually be more, and the model tends to, get more complex, and in some cases produce better results, right? As you feed in, as you add more parameters to that model. So it has a flexible structure that grows with the data, because so it can accommodate more models, right? And there are models that are able to do that. It's like your k nearest neighbor, what we refer to as KNN. You have your decision trees. Your decision trees can keep on branching out for almost to infinity. And then you have your random forest, which is often a combination of different other models. But then there is also what we refer to as ensemble models. Ensemble models, I think, are actually models that combine some of the advantages of both of these models, right? They are referred to as ensemble models. The trade-off, though, is interpretability and flexibility versus flexibility. And these are some simple examples, right? Are easier to explain what's going on, but as models become more complicated, they become a little more difficult, right? To really explain, like explainability becomes an issue. So in trying to solve classification problems, this is what a typical workflow of a classification problem would look like. First of all, we define the class label, and then we inspect the class balance. And what does it mean to to inspect the class balance? So for example, if I have 990 guys in a class, right? 990 guys in a class, and the ladies are just 10 in that class. That's an imbalanced class, right? So if I go ahead to go build a model with that model will be able to accurately predict the guys, but might not be able to predict the girls in that group, right? Because you haven't given it enough information about the girls to be able to predict the girls, because the number of girls in your, in your like your data ports is very imbalanced. So in some of those cases, it's better that you're working with 10 boys and maybe 10 girls, or 500 boys and 500 girls, for the algorithm to be able to learn what it means to be a boy, what it means to be a girl. And then you would have a model that is able to predict or make a distinction between a boy and a girl. So after you've defined those class labels, the labels will be boy, and then the other label will be girls. Now you want to inspect the label balance, right, based on the data that you have. Then once you have done that, the next thing you want to do is you want to split that data into training data and test data. And I did mention earlier in a previous video that normally, ideally, you should split that data in three, right? training data, validation data, and test data. But in some classifications, they put your training data and your validation data together. But one thing to make sure is to make sure that your test data is completely separate and does not leak into your training data. Because if it does, you might get a beautiful model, but when you go do inferencing or testing it on data outside your system, it's going to fail. So essentially split your data into training and test sets. Often the training data is a much larger, a percentage of the data. So it could be something like 80-20 to test data, or 90-20. You don't need a lot of data to test your results. Then the next thing, just like what we did in the case of regression, is to pre-process our features. We need to know what our features are and then pre-process them. Sometimes you have to combine things, delete some, do some kind of feature engineering there. Then number 5, you want to train the baseline classifier. What you're starting with, you want to train it first with the data that you have. And then you now go in to go evaluate the confusion matrix and the matrices, some of the things I showed us here. Let's go back a little bit where we were talking about, interpret your accuracy, precision, recall your F1 and ROCAU. That's you evaluate your confusion matrix and those matrices, and then you tune your threshold or model as needed. That's now in tuning this, that's where your validation becomes important, because you're trying to make our model better. And then the next thing is to now interpret the errors in the decision in the context of the particular decision. So this would be code, and again, you can literally open your Jupyter lab, and this will be code that can help you actually generate some random data, right, that you can use, generate some classification data, So this will be an example of a code like that. Your Skylearn, which is your package for machine learning, and then you import this particular class, make classification, and this is train test split. That's a module within your module selection method that is used to help you split that data into whatever ratios you want. And then this is where you do your classification, your data. There are 2 features here. And then you clusters by class 1, and then random state 42. And then this is you training your data, you split this, and then you get this. So you see the rest of the code, So we're going into logistic regression right now, right? And this is the code you can, and my whole thing is to go try this out, and then you are able to do your confusion matrix and then generate some kind of classification reports with this. This is where you fit your data, and this is you declaring a logistic regression method, that can help you do that. Notice where you imported your logistic regression model, and you got it from your sklearn machine learning package. So now we go to evaluation and decision consequences. Remember, now we're talking about the confusion matrix. What's a confusion matrix? what are the matrices, the imbalance. We're talking about the data being balanced. And then what are possible trade-offs? And those trade-offs, right, might eventually come down to what are the unique domain specific needs or challenges within your business. So a few things to understand before we do a further deep dive is understanding what these terms mean. So for example, when we say something is true positive, that essentially means that it correctly predicts something that is positive. So something is supposed to be positive and it does predict it to be positive. So that's a successful detection. So someone comes in with cancer, you run a scan, and then you pull that scan through a a cancer, an AI cancer model, and it correctly predicts that this person has cancer, right? So that's a true positive, which is a successful prediction of that disease condition. Now, if we have a true negative, this is also similar to true positive. It actually correctly predicts that, hey, this patient does not have cancer. So that's true negative. So notice the pattern. True positive correctly predicts positive. True negative correctly predicts negative, right? In other words, it's correct rejection. But then, let's say we have a false positive. Now that's where it begins to get dicey. So this fellow does not have cancer, but all of a sudden the system is saying, yes, they do have cancer. That's a false alarm, right? That's a situation, what we call false positive in data science and in machine learning, AI in general. So you predicted positive, which is why it's false. It's not true. It's said to be positive, but that thing is not correct. That's why we call it a false positive. So essentially, the consequence of that decision is that you create false alarm. And then you have a false negative too, So you're saying it does not exist when it actually exists, right? You predicted negative, but in actuality or in but there's actual positive. So that's what we refer to as false negative. So you missed a particular case, So it's like someone walking in, and they do the test, take the scans and everything, feed it to the model, and then the model says, oh, sorry, you can go home, you don't have cancer. That's a missed case, and that's dangerous. So understanding all of this can help us with the next steps of some of the things we will be looking at in the future. So one of the things to note is that metric selection is ethical and it's practical. So we talk about accuracy. These are different terms that you would use, different matrices that are used to evaluate, uh, uh, models. One of them is accuracy. It's best used when balanced and error, when classes are balanced and errors are similar, right? But if there is imbalance in that data, then it will throw you off, like I was mentioning, right? So it's generally hard. Like if your data is imbalanced, definitely this is not the best metric to measure it doesn't give you a full picture of what's happening to your model. So for each model, you might have all of this, right? And you need all of these matrices in most cases, but you need to pay attention, understand what picture each of them is building to you. And that's what the whole point of this slide is about. So let's say if we're trying to say, oh, we're trying to figure out the precision of this model, right? It is best when the false positive are costly. So what's our false positive again? Let's go back. false, positive, predicted, but actually it's actually, so in a case where you're raising alarm that doesn't exist, right? So that's when precision, when if we have a situation where a false positive can be costly. So for example, you go tell someone, hey, you do have cancer, but you will die in 2 months, right? One of the matrices you should be looking at, if you get a result like, you know, should be looking at your precision. Because when you give someone that kind of announcement, they could literally die because of the trauma, or they could end up go sell everything they have, and then you actually cause the problem for them. So the best metric that can actually help you figure out what's going on here, will be precision. The risk is that it might miss real positives, right? If you're focusing so much on the false positive. So recall, this is best when the false negatives are costly, right? It might create many false alarms, and then you have your F1 score. This is a metric that is a little more balanced, right? It needs, usually you build your F1 score using your precision and your recall. You need balance between your precision and your recall, you know. So the thing is, it can hide some business priorities. Again, that's why I said you have to look at all of these parameters to be able to see, have a fuller picture of the behavior of your model and the results you're getting. Then you have your ROC, AUC. It's used to compare ranking ability across threshold values. The problem with it is that because it's just there are charts and tables. Someone that is unskilled in the art might not really understand. It can feel abstract to them. And I think we would look at that when we begin to look at our Jupyter notebook. So the other thing I want to mention is threshold thinking. Classification models, and we talked about classification models where we deal in categories, right? They often output probabilities, So when it gives you a result, it's not giving you an absolute value. It's trying to say, hey, I think this is correct, and the probability of this being correct is 90%, for example. But you, as the model creator or domain expert, you need to be able to decide what the threshold is. So the default threshold of 0.5 is not always appropriate. Some people will choose 0.5. Oh, say everything lower than 0.5 is bad, everything higher than 0.5. And when I say 0.5, we're talking about 50% is positive. That's not exactly correct. So you can move that knob, right? That 50%, let's say it's a knob, you can move it upwards or downwards depending on the priorities of your business. And that's why I gave the example of doing a classification model, for example, where I'm trying to decide whether the emails that come into my email box are spam or they are not spam. Well, if a lot of emails that are not spam come through, the world will not end. But if I go make mistakes, right, with someone's life, right, or I'm building a driverless cars, right? And that driverless car is supposed to continuously make decisions about, oh, there's a child in front of me, or there is a human in front of me, and I know by this amount, this probability. In those cases, I don't have a lot of margin for error. So for cases like that, I might want to move my threshold to something like 99% or 98%. But if I'm dealing with email spam, I might be like, let's just make it like 70. Because if I move it to like 90 something, I might have a situation where some important emails that are supposed to come to me, it's now detecting them as spam, right? So that's how you tweak that. So it says lowering threshold, right, increases recall, right, but may reduce precision. In other words, and we are talking about your false positive and your false negative, for example, right? Your false positive, false negative. Um, oh, where did we have that? So that's what I'm talking about, right? Sometimes you have your false positive, false negative, as you lowering threshold can increase your recall, but may reduce your precision. So you have to be careful how you decide what your threshold is. And then raising threshold can increase your precision, but may reduce your recall. So I just talked about the email case. If I increase my threshold to like 99%, right? I might end up with a situation where it's accurately making sure no spam comes in, but you also might be making some mistakes where I have important business email, but it's sending them to the spam. So we have to look for the balance and look at how does it affect my business realities. So then we need to choose thresholds based on what consequences. The consequences might be different in different business contexts, and that's where your threshold thinking becomes very important. So, and this is a model for a decision tree classifier. Again, you can copy this right into your notebook and play around with it a little bit. So the models, this is a logistic regression model. I got a decision tree classifier and then a K9 classifier model. So essentially, we have three models here. The first model is picked from the earlier one because we already imported it in the previous slide, right? This is our logistic regression. So think of it, all of these code should be in one page on a Jupyter notebook. So essentially, we're looking at three different models and we're trying to compare their results: logistic regression, decision tree, and KNN. So it says for name, for a model in models. So I'm looking for each of these models within models, right? Per item, I want to be able to fit an XY, curve to see how each of them performs, right? And then I print out the name, either of the names, and then the classification report, which will be, testing the results using my test data. So next, we're going to go into clustering and unsupervised learning. We just finished with classification. Now we want to look at clustering and unsupervised learning. K means scaling, elbow method, and interpretation rules. So often, like I mentioned before, in unsupervised learning, there are no target labels, right? You're just feeding the algorithm your data, and it's supposed to make sense of it, right? By simply clustering, putting it in different buckets, right? So the goal is to discover structure. So it's going to look at every one of them and those that have similar structure. For example, the exam use case I gave you about a Montessori classroom where you have a lot of objects and these objects have different shapes: triangular, rectangular, circle, polygon, and all of that. So the idea of unsupervised learning is to discover the structure, what things are similar, and put them together. So the idea is not to predict a known outcome, but it's just to organize things based on similarity. So interpretation depends heavily on the selected features and scaling. So cluster labels, any labels that could have been put there are merely artificial. They require business or domain meaning. So the K means intuition. So the K means model. What's the intuition behind them? The idea is, for example, we choose a number of clusters. Let's say we have 5 clusters. So if we have 5 clusters, we choose 5 clusters. That would be like K. That would be like 5 different, K will be equals to 5. Then we assign each point to a nearest centroid, right? So we look at the distance between that to some kind of centroid that is closest to it. And then we recompute those centroids from the assigned points and repeat until the assignment stabilizes. So you're constantly looking at what is nearest to a particular centroid, which is a center relative to a particular data point, right? That's what you're doing. You keep doing that until, because that can help you figure out what and what are closer to each other, what and what object are closer to each other. You do all of those measurements, but it's sensitive to scaling and initialization and outliers. That's the challenge with k-means intuition, because it's better for you not to have outliers, things are close, but if you have some of the data, a few of the data that is out there, like it throws in confusion into the model. So this is you importing a k-means model, and then your standard scalar that can help with pre-processing, and then we've chosen what our features is. And in this particular case, you're actually using the Titanic data, which we talked about, very popular data sets from the Titanic crash that happened in 1920 something. So some of the input features will be age imputed, like the age of the passenger, the fare they paid, and then their family size. And then we said dot drop NA. This is essentially a method for dropping out, any data that is not a place where there is missing data, right? This will help drop it off on each of these columns. And this would help fit and transform the data, and then you introduce your k-means. And in this particular place, you've chosen that you have 3 clusters, a random state of 42, and your initialization, and then you try to use your k-means model to fit and predict that data, right? And then your clusters, this will be your new features, your cluster, and then you group by the different clusters, and in this case, I think there should be like 3 clusters, right? And then you take the mean of all of that. That's how you actually do your k-means clustering. So how do you interpret your clusters? You provide clusters using original feature values, not only scaled values. That's where you start. Do not assume clusters are causal groups. You know, uh, you don't do those assumptions. The system will have to decide what the clusters are. Validate whether the clusters are stable under different k values or samples. This would be better done in an actual example. And then we want to usually just go ahead and name the clusters, but you have to be cautious because you don't know what specific characteristics that the system has used to assemble them. So be careful. So for example, after clustering all of that, someone can come in and say, oh, this cluster is high fare, older passengers. You are not exactly sure, right? But it's going to be better than saying they are premium loyalists, for example, without actual evidence, right? So common pitfalls in your K nearest neighbor, uh, algorithm, it says using accuracy on imbalanced classes. Those are some of the things, and not just KN. In fact, all the other things, you don't want to go use accuracy, because accuracy is not a when you're looking at accuracy for an imbalanced data, it's going to give you results that are really, really wrong, and you might not. So for example, like the example I gave of 990 boys and 10 ladies. So on the boys' part, if 50 of them do not show up for school, right, it's still a small percentage of 990 of them. But if we say 10 of the ladies did not show up for school, it will go be something like 10 divided like by the sum of the boys and the girls, which is going to give us, something that's really, really very high, and you're like, oh, the ladies are very truant. No, it's just because the data is kind of imbalanced. Forgetting to scale features for KNN, K nearest neighbor, model. Sometimes we need to scale the features, or you are trying to confuse logistic regression with linear regression. They do completely different things. This is more, like what we did in the first place, and this is more separating things into categories. Your continuous outcome, and this is more categorical. Assuming clusters are real world categories, they are not. They are just things that the system have put together, so you need to interrogate them carefully. They give you real good results, but sometimes you need to interrogate and see what it is that the system has created. The other pitfall is reporting model metrics without explaining the consequence of those errors, right? And I did talk a little bit about each of those previously. So we are eventually going to go to the lab right now and see a few things, but then you have the slides with yourself to go through a deep, deep dive on some of the things that we already talked about here. These parts of the slides helps you with those deep dive. So I think we are going to stop with this right now and proceed later with the lab. So see you in the next video.
Okay.
All right.
Okay.